Before we get into all the details of how we analyze pumps and turbines and things, we're going to spend a little time just discussing the various kinds of machines that are out there. The first fluid machines were basically bucket wheels and screw pumps. Things like the Archimedes screw, which was invented in ancient Greece. Paddle wheels were developed by the Romans in around 70 AD. Later on, people developed windmills in order to harness wind rather than water. They also made life difficult for people like Don Quixote. Now, windmills are very useful because they can be built almost anywhere, but they have lower power than water wheels, and so some of their applications are a little restricted. In general, there are two fundamental categories of fluid machines, ones that do work on a fluid and ones that extract work from a fluid. So items that do work on a fluid include pumps for liquids. Fans are used for gases and produce very small pressure changes. Blowers are used for gases at moderate pressure changes, and then compressors are used for gases when you need a very large pressure change. Machines that extract work from a fluid are typically called turbines, and there's different classes of turbines as well. You can also classify fluid machines based on their function. Positive displacement devices force fluid movement using changes in volume. Dynamic devices, also called turbomachines, use rotating elements so they can perform or extract work without changes in volume. Now, today we use pumps all over the place. There are some links in the presentation here that you can see some more information about different kinds of pumps and things. Now, we're going to focus on pumps because we can assume incompressible flow. However, the same basic principles apply to fans and blowers. Once you start looking at compressors, then you need to start considering compressible flow behaviors. Centrifugal pumps consume about 5% of all energy produced in the United States. It's a big deal, and improvements in pump performance might be small, but because of the scale of their use, those small improvements have a large effect on the systems that we use every day. Now, gear pumps are a very common type of pump. It's often used in cars for oil pumps or automatic transmission. The basic idea here is that the space between the teeth of the gears has a volume that we can make use of. So if you spin the two sides of these two gears, you can use the space between the teeth of the gears to carry fluid around, and then when the teeth of the gears mesh back together, it forces the fluid out from that gap, and so you can push the flow that way. Vane pumps use centrifugal force to move these vanes. They're often used in power steering pumps and things like that. And then the vanes push the fluid along. Screw pumps, as we said, were invented in ancient Greece. The basic idea here is you're continuously elevating the fluid, but you have to be careful to make sure you have good seals, otherwise the flow can move out around the screw, between the screw part and the casing. Piston pumps basically use pistons to pump a fluid, and you have typically two pistons. So when one piston is pushing the fluid, the other one is filling. And then when it switches, and the next one pushes the fluid, and the first one fills to maintain a more consistent output. Peristaltic pumps are often used as fuel pumps or in heart-lung machines. You have a flexible tube, and you compress a part of the tube and then move the part that's being compressed to push the fluid along. Now, centrifugal pumps use a spinning impeller to add energy to the fluid. It's actually the most common type of pump, and they're very robust. Jet pumps make use of very high velocity jets to pull some low pressure fluid along with it. Typically, you would use a diffuser to recover the pressure to have a higher exit pressure. But the issue with these is they typically require a centrifugal pump to be used to produce the high velocity jet. Airlift pumps use the buoyancy of air to move a fluid. So when you inject air into the liquid, the buoyancy of those air bubbles is going to cause the liquid to move upward. And so when you do that, you can move the liquid using that kind of principle. Typically, these are very low flow rate. They're also very inefficient, and they require some kind of compressor or blower to provide the air. Axial flow pumps are similar in principle to centrifugal pumps, but the flow moves through it along the axis rather than changing direction to move radially. They're also called propeller pumps. Now, turbines extract work from a fluid. These types of machines are a $400 billion market every year, and it includes hydraulic turbines for things like hydroelectric power production, steam turbines, again, for Rankine cycles, or gas turbines for natural gas power cycles, and various other applications. We're actually going to focus mostly on hydraulic turbines for this class. Steam and gas turbines usually require compressible flow analysis. Even though the fundamental principles are the same, we can't make that assumption of incompressible flow, and it makes the problem significantly more complex. Now, impulse turbines are driven by a high-speed jet of fluid. For instance, the Pelton wheel that's shown here on the top picture in this slide. Reaction turbines use vanes, and the fluid accelerates through those vanes and produces rotation. And these are used for things like steam turbines or gas turbines. They're more complex, but they can also produce much, much more power.